Hello everyone, we have been given the segment to talk about Isaac Newton, who was a renowned physicist with discoveries in various fields of science and the main principles of physics, such as the description of physical laws and motion. And now we're going to talk about three of his laws, which were named after him, Newton's laws of motion. The first one was, every object in motion stays in motion unless acted upon an outside force, and every object at rest stays at rest unless acted upon an outside force as well. And his third law, which was that every action has an equal or opposite reaction. And now, to show you this, we're going to grab a beanbag and we're going to slide it across the floor, and thus measuring the distance, taking the time, and weighting the beanbag so we can actually later on calculate the frictional force, the applied friction, and find the coefficient of friction, which is called mu, and later on also find the acceleration and the net force.
We are testing the hypothesis of if Newton's first law states an object in motion will stay in motion unless acted upon an outside force, then the unbalanced force of friction will make the bag come to a stop.
The purpose of this lab is to prove that an object in motion stays in motion with the same speed and in the same direction unless it gets affected by an unbalanced force. Moving objects would eventually stop moving, but a force was needed for it to move. Newton's laws are applied to objects which are made ideal as single-point masses, in the sense that the size and shape of the object's body are looked down upon to focus on its motion more easily. This can be done when the object is small compared to the distances involved in its analysis, or the deformation and rotation of the body are of no importance. In this way, even a planet can be idolized as a particle for its analysis orbital motion around a star.
My materials are a calculator, ruler, beanbag, the phone, and stopwatch. Hi, my name's Leo, and I have gathered all my materials. I have a beanbag, a timer to time how long it takes, and then a meter stick to show like the distance from the beanbag from the blue line all the way to wherever it goes. Here I go. Now I'm gonna be sliding the beanbag from the blue line, and my partner is gonna time it, and then after, when it's all settled and done we're gonna measure how long, or how like the distance from it. Here I go.
Go. Go.
We're gonna have some like crazy.
Determine the frictional force of the sliding beanbag. We have to use these two equations, and we will plug in for delta x, the average time. This average time, time, and average distance. So when I calculated the average distance, I got 35.83, that equals 1/2 VF, which because it stopped would be 0, plus VI equals T. And I got 1.92 for this one. And then I would just distribute. So it would be 1, VI 0.92. Divide it to both sides. And you would end up with an initial velocity of 37.32. And you're going to use this number and plug it into the next equation. So VF again is 0, and VI, which is this number, is 37.32, plus A, and time, again, 1.92. And then just do the algebra. Divide it by your time. A would equal 19.43, and it's negative. And it's okay if you get a negative answer because you're trying to get what is needed in order for the bag to stop. Newton's first law states that an object in motion will stay in motion unless acted upon and outside or unbalanced force. The unbalanced force in this lab is friction. The friction will cause the bag to come to a stop. Coming to a stop is not Newton's first law, but it's the second law. It's the second law that states that an object in rest will stay at rest. In our lab, we predicted that if a bag is thrown, the faster the bag is thrown, the sooner it would come to a stop. And we were correct. Because of the friction, of the higher friction between the floor and the beanbag, the beanbag stopped faster than it would if you were to throw the beanbag at a slower speed.